This presentation is intended for the course CDA 5106 at University of Central Florida. My name is Rick Lineker. In this lesson, we are going to cover computer abstractions and technology. So the computer revolution continues, obviously. We can see it everywhere. But underpinning this progress in computer technology is Moore's Law. And you actually see a lot of different figures thrown around about Moore's Law. Originally, he said that every 2 years the number of transistors in integrated circuits doubles. It did get changed over time. At one point it was a year and a half, every year and a half. At one point it was even every year. Right now, so the accepted length of time is a year and a half. So we say Moore's Law tells us that every year and a half the number of transistors or the power in a integrated circuit doubles. Well, what this does for us is provide a lot of amazing applications. Novel applications now have become feasible that 20 or 30 years ago we could only just imagine. Let's start with the computers in your car. Your car is basically completely controlled by computers. Now, that's maybe good, maybe not so good. If you're like me and you grew up working on cars, I can no longer just take out my timing light and change the timing of the car and change the points and stuff like that. I've got to actually have the gear to plug in and do analysis through the computers and stuff. So that's kind of the downside, but the upside is cars last a lot longer. These computers really make the cars more efficient. The computers allow technicians to figure out what has gone on, and they keep a history of issues that have been recorded. Now, there has been people who have pointed out that these computers can be hacked, and there have been suspicions that some people's computers in their cars have been hacked from a distance. That's sort of on the speculative side, but I've seen some evidence that it's possible. And in today's world of cybercrime and hacking, it's not too surprising. Another thing that you're probably well familiar with is the technology in cell phones. Obviously, a cell phone is a computer, and it's not just a cell phone anymore, although some people still do buy these flip phones and that don't have many apps at all, and even the flip phones have, you know, a certain number of apps that you can use. But you know, my iPhone 6, actually I've got an iPhone 6 Plus and I've got an Android, and they both are computers faster than my original PCs back in the day, and they have more memory and they do more, and they're totally connected to the world. I mean, I know everything because with my little phone I can go and do a Google search and find out virtually anything I need to know. Unfortunately, I haven't found the website that will tell me what Saturday night's lottery numbers are, but I'm still looking for that one. If you know it, please let me know. So cell phones have really been sort of at the forefront of this technological advance. The fact that you can have a cell phone that does almost anything, track flight patterns, track weather patterns, I mean, they are amazing. The Human Genome Project definitely was something that couldn't have been done without computers and fast computers. Not only fast computers, but fast computers with fast algorithms. So the people who developed the Human Genome Project software actually spent a lot of time before they even ran it creating the kind of algorithms that would be really fast. And if I actually teach computer science too a lot, and we spent a lot of time in those. I spent a lot of time in that class talking about how to optimize algorithms. Well, the World Wide Web obviously is huge. I mean, we all take it for granted now. But the only way that it's possible is with this huge explosion in technology, in computers. And they sort of feed off each other. You have this big revolution in computers, which feeds the World Wide Web, which, because this is so big, everybody's able to learn things. And then there are more innovations, and then the more innovations create a bigger World Wide Web and so forth. So they feed each other, World Wide Web and the computer revolution. Search engines are probably more advanced and more sophisticated than you might think. If you've ever had a database class, the search engines just don't do a select star from search data where whatever search term equals. It's not your normal SQL that they're doing. They're doing the most amazing natural language processing on your search terms. They're looking at your search history to find out what you might, to better interpret what you're looking for. The search engines of today are amazing. Besides that, computers are pervasive. They live in refrigerators and toasters. I mean, they're in almost everything you can imagine. So we have different classes of computers, and let's go through those just to kind of define them right now. Most of us are familiar with personal computers. Although most of the students I have in class don't even have personal computers anymore. They either have maybe a laptop or a notebook, or now it's more common just to have a tablet and possibly a phone combination. But personal computers are general purpose, variety of software. It's the kind of thing that the consumer is going to buy so they can play solitaire, so they can surf the web, so that they can use Microsoft Office, so that they can maybe play games. Although most real games, such as say Call of Duty, require specialized computers. But these general purpose computers is what most everybody buys, like the Dells, and they go to Walmart or Best Buy or wherever. So they do a little bit of everything. However, they're a cost performance trade-off. There's always something you give up. People don't want to go to the store and spend $2,000 or $3,000 on a computer anymore. Although my first computer was about $4,000, and it really was not very good either. But there's this cost performance trade-off, and consumers are very cost aware. So that's why these things are really general purpose. They just don't have these high performance video cards and lots of memory and stuff like that where you can do some really great things. So I normally, personally, for my development boxes, I don't buy these general purpose computers. However, I set up a lab here in my office because I recently wrote a whole gaming enterprise level gaming system. And so I needed some normal computers to test. And I went and I bought some refurbs, and they were like $200, maybe $250 with the computers and the monitors. So really inexpensive to get these computers. So server computers are the next class that we're going to talk about. And server computers you rarely see unless you're network admin. I should tell you a funny story. I was doing some consulting for Thomas Bus in High Point, North Carolina. And most of the server rooms are locked down. You can't even look at them, much less get in them. And I had to update one of their servers. I was doing some custom software. And the network admin pointed, he said, there's the door over there. And like the door was ajar and you could just walk in. And so I walked over to the computer I was working on and updated it. Really funny, but that's not the norm. Normally these server rooms can't be entered by anybody except the people who are like network admins or the IT people who are maintaining them. But these computers are high capacity. They have huge performance, huge storage space. They're very reliable because they have redundant systems. They have redundant power supplies. They have redundant hard drives. Anything that can fail, they try to build redundancy in for. So they're really high performance computers. They range from small servers to building size. Most, though, of what you normally think of for these hosted servers, they're about 19 inches, and they slide into a rack. So they're really not huge. They don't have a monitor or a keyboard or a mouse. And what you do is you walk to a central place, and you use what's called a KVM, a keyboard video mouse switch, and you can drive them from this central place with the KVM switch. So supercomputers are sort of the elite of the elite. They're the computers that do the really cool things. They're high-end scientific and engineering calculations. And very honestly, they're also the things that the NSA are using to crack encryption codes. That's different than the iPhone they tried to crack, because that iPhone that the FBI couldn't crack, it's because that was a hardware thing that was going to lock out after a certain number of incorrect tries. But the NSA, they can take all the time they need to crack an encryption code or something, as long as there's no sort of timeout like the iPhone had. So these have the absolute highest capacity. There aren't many of them out there because they're so expensive, they're so specialized, and so you just don't find many. You find them usually at places like MIT or research universities, and so you might be able to purchase time on some of these. It just depends on the supercomputer itself and what the owners want to make available. And the last category are embedded computers. And these are really small computers that live within, say, appliances like your refrigerator or your toaster, or maybe your stereo system, or maybe inside of a monitor or something. These are really small computers that have a really limited scope of functionality. Okay, and so they're hidden as the component of another system. And since they're so small and so specialized, and they're within another system, there are really monumental power and performance and cost constraints. For instance, the power, that you can't have one of these things use up a bunch of power, otherwise it's going to potentially rob from battery life. The performance is not usually very good, just because it's so restrictive. However, it has to be the best possible, so you can't say write in a really high-level language. Normally, the code that's used is either assembly or possibly C, just to get the best performance possible. And the cost of these has to be low because, here again, it's embedded within another device usually. So this represents the post-PC era. And this is kind of an old slide. It goes back several years. But nonetheless, it's valuable to get a graphical representation of where things have gone. You notice it goes back to 2007. And cell phones are increasing. And that's normally for the people who just don't want a smartphone. Like my dad is one person. He's got a regular flip. That's all he can handle, and that's all he wants. So cell phones are still available, and they still sell them. PCs, you can see, is one of the next groups. The rise in PC sales is not very dynamic. That's because most people don't want PCs. They would rather have a tablet or something that they can carry around with them. The only reason people are still buying PCs is, well, I buy a powerful PC because it's my development box, so I have a specialized need. Or maybe there's a lab in an educational institution, or maybe there's a library. So there are reasons people would buy PCs. But I'll be really honest, they're not that convenient because they sit at a desk and you're not mobile. You can't even walk around your house with them. Now I have a laptop I carry around, but so here again, it's still pretty limited because my laptop is fairly low powered. It's actually 5 years old. Smartphone sales are the leading sales growth category. They're experiencing the fastest growth of all these categories. And that's because everybody wants a smartphone. I have two of them, and the reason I have two of them, an iPhone and an Android, is because I write apps, and because I write apps, I need to be able to test it on an Android and an iPhone platform. But smartphone sales are practically going through the roof, and this is an older chart. Now, I don't know if Samsung had a damper with their battery debacle recently, but tablets actually kind of peaked out. And tablets encompass, say, the Kindle Fire, the Android tablets, the iPad. Even Microsoft has a really nice tablet. As bad as Microsoft blew their smartphone foray, they've done a really good job on the Windows tablets, I think. So this just gives you a comparison of where all the sales are and where the actual growth in sales is. Notice that the growth in tablets is coming down. I think one reason is because the smartphones have gotten large enough that um, you kind of don't even need a tablet. I've got an iPhone 6 Plus and it's got a really large screen. So, carrying around a large tablet doesn't make quite as much sense for me. So personal mobile devices, these are the things that are battery operated, they connect to the internet. Basically, they're untethered, which makes them really desirable, okay? The fact that I can walk around anywhere, I can either get Wi-Fi or 3G or 4G, I'm in business, right? They cost several $100s, although I've bought Android tablets that were like 90 bucks. So hundreds of dollars, most of them do, but you can get some really low-cost tablets. So this category includes smartphones, tablets, electronic glasses. And I think that the Google glasses that we had so much press about a number of years ago, I think Google was just setting us up. I think that they knew that the Google glasses weren't going to be a long-term thing. I think basically they were just trying to get answer some questions that they had in their research and development. I don't think that the electronic glasses are gone. I think that after the Google glasses, I think they've learned their lessons, and I know, and they were on purpose trying to sort of probe the market. I think they're going to be coming back sometime soon. Maybe not in that form, maybe in another form. My theory is that you're going to get a chip behind your ear and iris implants. That's probably where all this is headed, and I'm serious about that. So maybe the glasses will never show up. It'll be the implant behind the ear and the iris implants. Cloud computing now is really hitting its own stride. You have these warehouse scale computers that just store enormous amounts of data. A really big example of that is the facility the NSA built out in Utah. I mean, it's handling all of our emails and texts and phone conversations. I mean, imagine the staggering amount of data that is. Another area of cloud computing is software as a service, or sometimes we say SaaS. This is absolutely huge. This includes applications such as Microsoft Office. Microsoft Office used to be a standalone application that you put on your computer, and it was, that was it. Now Microsoft Office is something that half lives on your computer and half lives in the cloud. And without the cloud part, you can't do it. So it's software as a service. They've gone to this subscription model, and really it's a lot more lucrative for them. It's guaranteed revenue. For instance, if they sell you Office, they sell it to you once, and maybe you'll buy it again the next version update. But now they are going to get you a subscription fee every month or every year, depending on how you pay for it. Even Photoshop has gone to this. The Photoshop, and I'm not an expert, I don't use Photoshop very much, but they've got this creative studio or something. Here again, please, if I got that wrong, I apologize. But even Photoshop now is this sort of hybrid where you've got part of it running on the device and part of it up in the cloud. And this third bullet point sort of summarizes that for these applications, these sort of new generation applications, part of it runs on your device and part of it's up in the cloud. Examples of this are Amazon AWS, Google Compute Engine, and Microsoft Azure. And I actually have been using Azure a lot myself. I live normally in the Microsoft world, so Azure is really good for me, and it turns out it's very consistent with the way I attack things. So now let's say a word or two about performance. So the first level of performance is the algorithm, and here again, going back to computer science too, we spend a lot of time talking about how to optimize algorithms. For instance, you can do a simple search, or you can do a binary search. A simple search is where you search the whole list, like you go sequentially, and you search the list. Well, a binary search is where you split the difference, and if that's too great, it's kind of like playing guessing a number. You start here, and if that's too great, you go here. If that's too little, you go here, and so forth. You're kind of splitting the difference. Or binary search trees, which operate in a log n time. So what happens is if you have an algorithm that is really, really efficient, then you're executing fewer and fewer operations. And that's what an algorithm is supposed to do. It's supposed to reduce the number of operations to a minimum. Now, an algorithm is actually independent of the programming language or the operating system. So an algorithm you can apply the same algorithm to any language and any algorithm, any operating system. Now, you probably can't apply any algorithm to the logo language or the processing language, but to most languages you can. So once you've established the algorithm, then the programming language comes next. The programming language is basically the source code is human readable text, which then the compiler takes and converts to some sort of machine code or some sort of intermediate code or something. And so the second part of this equation is that you have this programming language, and it is going to do its best to convert the source code or human readable code into the fewest number of actual machine instructions possible. Okay, so the more efficient it can convert the source code, into machine instructions, the fewer machine instructions actually get executed. So the algorithm means you have fewer operations. A more efficient programming language means you have fewer machine instructions for those operations. And then we hit the third point. The processor and the memory system are going to determine how fast those instructions that the compiler created are executed. So a fast processor is going to execute those instructions a lot faster. However, a fast processor without fast memory is going to be hamstrung. So they both need to go hand in hand. The memory system and the processor need to be compatible. Otherwise, one or the other is going to still slow things down. Now, at a certain level, the I/O system could potentially be a performance bottleneck. For instance, if you're going to the hard drive a lot and you're running a 5400 RPM hard drive or something, then it's going to slow you down. If you're running a 10,000 RPM hard drive, then it's not going to slow you down nearly as much. In fact, it'll probably be pretty fast. So the I/O system may turn out to determine how fast your software is operating. So these are the four things that we think about when we talk about performance. When we talk about the performance of an application. Okay, so here are 8 great ideas, and these ideas are what you want to think about when you're trying to engineer applications or systems. Well, design for Moore's Law, meaning that you know that you're writing this application today on today's hardware, but tomorrow the hardware is going to be faster, and then the next day the hardware will be even faster. So what you want to do is you want to realize, well, okay, it's running okay today, but in the next generation hardware, it'll run that much better. And so don't say it's only going to run as fast as it runs today. Make sure that there's always something built in that when you get extra cores or when you get extra memory, your applications can dynamically adjust to those. And we're going to be talking about parallelism pretty soon. So when we do, we'll talk about sort of how you can sort of build that in and have your application dynamically adapt to the number of cores you might have. You also want to use abstraction to simplify your design. Now, you can go way overboard on the idea of abstraction, but in general, abstraction is a way to say, okay, here's a task. I'm going to say, load in a disk file, maybe it's got some text data or some CSV data or something like that, parse it out, and get, say, maybe do the standard deviation of all these numbers in the list. Well, if you have to worry in your mind about, okay, first I have to open the file, and then I have to read each line at a time, and then I have to go and parse these lines, and I've got to split them into the various columns, and that's a lot of detail. What you really want to do is abstract it to a single, say, process, such as read file and calculate standard deviation. So that is an abstraction on the entire process. The entire process has a lot of detail. And if you can abstract things out like that, your software or system design gets a lot simpler. And this is whether you're a programmer or a software engineer or just an IT professional who's trying to design a system. And we'll come back to abstraction shortly. We do a little bit more detail on that later on in these slides. So make the common case fast. And what this means is some of you may have, especially if you had me for computer science too, some of you may have seen like loops, for loops, and sometimes stuff happens within the for loops. Well, the idea is the stuff that's in the very, very middle of those for loops, you should concentrate all your effort on making that stuff fast, because that might happen many, many, many more times. This one thing over here that only happens once, but these small pieces that happen many, many, many times, that's where you need to focus all your energy. You need to make all that stuff fast. So when it says make the common case fast, what that is, you take the things that happen a lot, those little things that maybe not take very long, but when they happen a lot of times, it adds up. Focus on making those fast. Performance via parallelism, and I actually kind of specialize in parallelism. I write for Intel, and I write a weekly column on parallelism and vectorization. So the idea is that you can take any task and break it up into subtasks and perform them all at the same time. That's parallelism. And we'll be talking about parallelizing for loops, but now the software tools, the compilers, are so smart that with a few compiler directives you can actually parallelize a for loop with almost no effort. Performance via pipelining. Pipelining is a way to sort of push stuff through. Take for instance the analogy of an oil pipe, and you're pumping oil from here, maybe crude oil, from here to where we're here. And as you push it through, you're doing your best. You're just pushing it through, pushing it through. But if you can have substations along the way, okay, substations like there's a small section and you got a pump specially for that. You have a small section here. There's a pump specially for that. If you have this pipeline with subsections, everything works better. So this can be doing something, this can be doing something, and they can be doing their own thing while the whole process is in progress. A really good example of pipelining is with your GPUs. And your GPUs essentially, your CPU normally starts off with calculating the primitives that are used to draw this thing. Then they calculate the vectors, and then they calculate the vertices, and they go through and they do the shaders and so forth. So a GPU has a number of steps that happen, but this is what's known as a pipeline, because as this guy is calculating maybe the primitives, and this guy is calculating the vertex, and this guy is doing the shading and stuff, they're doing them all separately so that you don't get hung up in this sequential, okay, first I got to do this, then I got to do this, then I got to, oh, finally I got an answer. Well, no, it's he's doing that while he's doing that while he's doing that while he's doing that. So that's the idea of pipelining. And the GPU, to me, is one of the best instances of how pipelining can work very well. Performance via prediction. Here, you want to sort of dynamically predict what's going to happen. Hierarchy of memories. We talk about this kind of in depth. And essentially, the very most, the closest memory is the actual CPU registers. And then after that is the L1 cache, and after that is L2 cache, however many levels of cache you happen to have. Then from that you get random access memory, and then from that you get say your hard drive, your virtual memory. Then from that you get the say memory such as maybe CDs or something. So there's this hierarchy of memories, and knowing how that hierarchy works, knowing what hierarchy you have to work with, knowing how it works and how to take advantage of it will definitely help you design a system. Dependability versus via redundancy. Now, I've already talked about redundancy when we talked about the server computers earlier. And redundancy is, you might have 2 power supplies, you might have 2 hard drives. In fact, almost all servers are going to have multiply redundant hard drives. And so this idea of redundancy is going to provide significant dependability to your servers and your machines. So your program is going to be known as application software. Examples of application software are Internet Explorer, Microsoft Office, Solitaire, Minesweeper, so forth. This is application software. So it's at a very high level. It's normally written in a high level language. In fact, it's rare that anybody's even going to write in C. So maybe Java or C# or VB.NET or something like that, or an even higher level language. And that's normally what we teach here at UCF. Probably what most of you do is application software development. But there's actually a lot more that goes on down below that. So system software is the layer below your application software. Without the system software, your application software wouldn't really be able to do a whole lot of anything. So what happens is the compiler, as we've already talked about, translates the high-level code to machine code. Now, that's not necessarily always the case. Sometimes there's like a two-step compile. The compiler in languages such as Java and C#, it goes from source code to an intermediate code. The compiler goes from source code to intermediate code. And then the Java, the JVM, the Java virtual machine will take it from that intermediate code to the actual machine code. And .NET will take the intermediate code and take it to machine code. And there are really strong reasons for doing it that way, having that two-part. And so what happens is you get this intermediate code, and it's called a just-in-time compile. And when you run the software, it actually takes it to machine code. But since it's already kind of pre-digested or pre-compiled into this intermediate code, it's not really it's really a fast compile process. But let's just sort of go back, sort of take a step back, and we'll just sort of oversimplify this and say that the compiler translates the high-level code to machine code. Okay, and you will realize that there in many cases is this intermediate step. So then the operating system provides services. The services such as sort of open a file, read from the disk, store something into memory, send a package over the internet or something like that. So the operating system services are handling I/O, such as file I/O, network I/O, mouse I/O, video I/O, and so forth. It also manages memory and storage. So if you've ever done a malloc or a new, that's where the memory services come into play. When you allocate memory in your application software, it's going to actually make these system calls to give you a chunk of memory that you asked for. If you're unlucky, though, you won't get the memory, and your program might crash unless you've error trapped it. Okay. Also, the services provide scheduling tasks and shared resources. Scheduling tasks can be sort of multi-threading or timers or things like that. Very important. I've written so many pieces of software that rely on multi-threading, and without multi-threading, they would be really not very good pieces of software. So these scheduling tasks are hugely important for software that operates in a modern world. Then below the system software comes the hardware. And the hardware is the processor and the memory and the I/O controllers and the interrupt controllers and all that kind of stuff. So this is kind of the hierarchy, and you see a diagram here. The outer ring is the application software, and then the system software, and then the hardware. Now, what's interesting is that in the Windows operating system, they actually separate the system software into 3 rings. It's a ring metaphor that they actually use, and each ring has a larger degree of protection. So ring 0 is going to be almost impossible to get to, providing security and reliability for the operating system. And the outer ring, ring 3, is going to be a little easier to get to, a little easier to use, not quite as mission critical as ring 0. So the system software can actually be segregated into multiple rings itself. So let's talk about program code now. We have a high-level language, and I know here it says high-level language program in C. C is not really a high-level language. It's really, You might think so, but a higher level language is actually C# or Java. The C language is one of the most low level languages you can get before you get to assembly language. But so let's sort of play along and pretend like it's a high level language. It's higher than assembly for sure. But you have a level of abstraction closer to the problem domain. In other words, if you're programming in a higher level language, you are dealing more with the problem rather than how you talk to the hardware and how you sort of interact with the data. And really, that's that whole idea of abstraction. We want to solve a problem in programming code. We don't want to get mired into the nitty-gritty details. So that's why we are going to use higher level languages. That's one reason. Another reason is they're faster than programming in an assembly language. They provide for productivity and portability. A lot of times you can take a C program on this computer. Like one of my students in this class, who's in this class this semester, Derek, we actually are swapping C code back and forth between, I'm working on Windows and he's using GNU-C on Linux. And it's fine as long as you've sort of planned for it. Assembly language, though, is actually a textual representation of machine instructions. So assembly language, there's a really tight correlation between assembly and machine code. Assembly directly translates into machine code. Now, you might ask, well, could you get better performance if you just went ahead and wrote assembly code rather than writing in C or even a higher level language? Well, I'll relate a story. I was writing a book, a C++ book, and my technical editor happened to be a Microsoft engineer, as it were, and so I was trying to do something and get as much performance as possible. So my inner loop, like we talked about, make the stuff that happens a lot as fast as possible. So I wrote my inner loop in assembly language. In the Visual Studio compiler, you can do inline assembly. And he wrote me this scorching email, and he said, look, if you think in this day and age with our sophisticated compilers that you can outrun the compiler by writing assembly language, you're mistaken. And basically what he was saying is that the compilers today are so good that even if you're pretty good at assembly language, which I am, that the compilers are going to beat you almost every time. Unless you have some case where, especially in graphics, I've done a lot of graphics programming, low-level graphics programming. Sometimes that might be one time when he would be wrong, but almost always he's going to be right. So it would be a mistake, except in this class I'm going to teach you about inline assembly. So it's not for performance, it's just for instruction. But the compiler is almost always going to produce really good assembly code. And really good assembly code then is always going to give you the best machine code. And remember, before we said the best machine code was always going to be the fewest instructions to perform a task. Okay, hardware representation. Once you assemble it, it's just going to be ones and zeros, as you can see here. So you go from a C language to assembly language, and then the assembly language directly translates to the binary. Now, I also want to point out that the C compiler can actually, you can give it specific you can give it specific hints on how you want it to optimize. For instance, with the C compiler, you can optimize for size, so you make your program smaller, or you can optimize for speed, so you optimize so it runs faster. So there are different ways actually to optimize C programs. Or you can turn the optimization off and it won't do any optimization. It'll just give you a basic straightforward, here's what I think you should do. So I just want to point out that there are lots of optimization tweaks in a C compiler. So this slide is pretty interesting. It sort of graphically depicts the components of a computer. So it's got this picture here, and you have the compiler, and it's creating these codes. Notice the interface. That's really the API. The API is sort of the window into the operating system services. Okay, without the services, like I said, your computer program isn't going to do you a whole lot of good. Within the computer, you've got the processor, you've got controllers, things that are controlling the processor, and you've got a data path. And we do get into quite a bit of detail on data pathing. You have input and output. So all computers have essentially the same sort of parts. They've got a processor, they've got memory. Not all of them have a mouse. However, they also will service a mouse of some sort. Desktops and servers, embeddeds aren't going to service a mouse unless you do something special. They all have I/O, right? Um, and it's going to depend. Most desktops and servers are going to have display, keyboard, and mouse. Remember, I said that the server, you need to go to a KVM switch to access that. Um, Embedded may or may not have display, keyboard, or mouse, just depending on the situation. A lot of times, though, if you've ever worked with a Raspberry Pi, you can plug in a display into it, or you can just not have a display. All of these are going to have some sort of storage devices, whether it's a hard drive, a CD, DVD, flash, ROM, EEPROM, or whatever. Most of them are going to have some sort of network adapter, because in today's world, if it's not communicating, so maybe your toaster might not need it, or your refrigerator embedded might not need it, but almost everything is going to have some sort of network adapter, whether it's Wi-Fi or Bluetooth or just a regular network card. So now here we're going to dig a little deeper on this whole idea of abstractions. This is a big picture on abstractions. So abstractions help us deal with complexity. We're going to turn a whole bunch of really complex details. We're going to ball them up, and in object-oriented programming, sometimes we call this encapsulation. So we're going to ball up these details into one abstract concept. The abstract concept might be something like ask the user for his information. And that ask the user for his information might encapsulate, such as, first display a form with all the information, let him type it in, maybe check all the data to make sure he's accurate, like maybe an email is an email, a telephone is a telephone, and so forth. So what you're doing is you've abstracted to this higher level idea, and that is going to help you design your system, whether you're an engineer or just a designer or an interface person. Regardless of your technical sort of role in this, abstraction is going to help you. Then there's an instruction set architecture, and this actually abstracts the hardware and software interface. Okay, so say I might have to make a call out to something that says open a disk file or something. Okay, the application binary interface, sort of the next level of that. Finally, the implementation is everything below that. So what are safe places for data? None. No, really. Main memory is going to be volatile under most circumstances, unless you're using static RAM. And it's so volatile that not only when you turn it off it all goes away, but the RAM in your computer has to refresh every number of microseconds. So it's dynamic to the point that if you didn't have that refresh cycle, even if your power was turned on, your data would be lost. So that's the most volatile memory is RAM, or I should say dynamic RAM. The static RAM is a different situation. So non-volatile secondary memory is like a magnetic disk. That's a floppy, which we don't have anymore, but a hard drive. Hard drive is still magnetic for the most part. Flash memory, which we all know. Even flash memory. I ask students for flash memory, and most of them don't even carry them anymore. They're putting everything up in the cloud. SSD, optical disks. These are all pretty safe, but they all have vulnerabilities. Magnetic disks have vulnerabilities to, say, magnetic fields, such as maybe an air conditioner that's misbehaving, or who knows what, or maybe someone just put it next to an old CRT or something. Flash memory, maybe someone steps on your USB drive. SSD is pretty safe, but still you can have glitches. Optical disks, you can have scratches and cracks and stuff like that. So they're non-volatile, but they still have their vulnerabilities. Networks, communication, resource sharing, non-local access. So the idea of a network is that I might be here and you might be in New York, and our computers are going to function as if they're right next to each other. Now, depending on the bandwidth latency, that may or may not be true, but that's the idea of the network, that we have tightly coupled, tight coupling, so that they're operating together. But there's this other idea called loosely coupled networking, which means that maybe my connection is slow, or maybe my connection is off for right now. But if I'm using some sort of a loosely coupled software architecture, then it's going to look for when that connection is back again, and it will complete the transactions that it originally wanted to complete. Loosely coupled was really in vogue when COM+ first came out in the early 2000s. And a lot of times people don't think of loosely coupled architecture like they used to. It's a really good idea. Basically, the difference between tightly coupled, it has to happen now, it's going to happen now. Loosely coupled means if it can't happen now, it's going to wait until it can happen. And so it actually takes a lot of effort to create loosely coupled architecture. That's probably, COM+ used to take care of some of the nitty-gritty details for it. And COM+ is sort of a thing of the past now. All right, local area networks, say maybe in the same room, the same building or whatever. Wide area networks, the internet. There used to be this idea called metropolitan area network too, which was, say, a city or a campus or whatever. Largely that's gone by the wayside. It just kind of lost its meaning. Wireless networks, which we all have in our houses, Wi-Fi, Bluetooth, cellular, all these are types of networking. So we have some math that we do to help us calculate an integrated circuit's cost. And the electrical engineers do a more detailed treatment of this, but we're just doing this to give you a sort of a high-level view. So we can calculate the cost per die as the cost per wafer divided by the dies per wafer times the yield. And dies per wafer is, let's say you take a wafer and you punch in a die for each one of the little integrated circuits that you're going to cut out of it. And so dies per wafer times the yield, that's going to give you the cost per die. So the dies per wafer is going to roughly equal the wafer area divided by the die area. And the reason it's only going to roughly equal that because if the die is not exactly square, then you're going to have some wasted area around maybe some rounded edges, or maybe it's completely round or whatever. So it's just an approximation. So the yield is going to equal 1 divided by 1 plus defects per area times die area divided by 2, all that quantity squared. So as you can see, this is going to produce a nonlinear relation between area and defect rate. Okay, so the wafer cost and the area are fixed. Okay, so you're going to order these wafers, or you're going to purchase these wafers, or you're going to manufacture these wafers, or whatever. And the defect rate is going to be determined by the manufacturing process, such as, you know, how far did you go to have cleanliness in the clean room, and, you know, what kind of temperature range did you build in, and stuff like that. And the die area is determined by the architecture and circuit design. So now let's talk about how we would define performance with kind of a metaphor here. We have these airliners, Boeing 777, 747, the Concorde, which isn't flying anymore, and the DC-8, which is a pretty old aircraft. So in the first one, you talk about passenger capacity. Well, it looks like the 747 has the best performance, right? It carries the most people. 777 is the next because it carries the next most people. But then if you go to the next graph, the cruising range, the DC-8 goes almost twice as far as all the other, or actually it does go twice as far as all the others. So that may have the best performance. Then you look at cruising speed, and the Concorde is pretty fast. That's why people liked it. That's why it was so expensive. That might be why it is no longer flying. And finally, passengers times miles per hour. Looks like here again the 747 is great. But now, which of these has the best performance? Well, it depends. You know, they asked Bob Dole, boxers or briefs? You know what he said? Depends. So it depends on what you consider best performance. Now, if you had one of these graphs, if all the graphs had the Boeing 777 with the best numbers, or the 747 with the best numbers, it would have the best performance. But best performance means, what are you trying to do? So let's say you have an application that you're designing or you've written, and the application maybe it does a lot of, say, 3D rendering. Well, at that point, you don't necessarily care about the hard drive speed. You really only care about the GPUs and just the math, the math and how it's going to render to the screen and all that kind of stuff. So which computer has the best performance depends on what you're trying to do. Performance is a measure of your objective and your outcome.